So, March the 7th, 2023, let's start problem 4. At least part A and B, which seems to be pretty routine. Of course, I should have written proposition 11. Here we are. And we use it progressively. That is to the kth. There's no problem in making the induction. So B So first I define h of x equals x dot w to the kth e minus pi t x x dot x. Now that's not a good idea. It's the Fourier transform with respect to t, of course. So it should be a function of t. So it was possible to get confused here after all. So, and of course, it doesn't state in the proposition, but I assume the situation of proposition 11, meaning that the function is a function of fast decrease. So does that mean we have to do it the opposite way? So, but then this guy is its own Fourier transform. So that's not so difficult. Not necessarily. There's some constant that I need to find. When I studied this in Rudin's book, they made a measure so that the Fourier transform was an isomorphism or isometry. No, an isometric map. That was very nice. Oh, but this is just the kth derivative. Oh my God, silly, silly, silly. So this is to the kth. And then there's a factor 2. I mean, if we do it once, oh, and there's the pi, of course, it's dt. Oh my God, what am I? I'm confused here. it's a function of x, so it's not a function of t, it is a function of s, of x. So I just got very confused. And then this will give us problems because the first one holds, but then the next except for a factor 2, of course, but now let's do the induction step. First we differentiate this guy. And then x differentiated times w, that's w squared. And then the other part comes minus 2 pi t w times x to k plus 1 and all that times if that is the induction step, then I have no idea what the result will be. Yeah, I have to make a break here. I'm totally confused. All right, a little break, and then I read the problem again, and it says that w is 1 point r, and that means that w squared 1 point I times 1 point I equals 1 squared plus I squared equals naught. So that means that it simply becomes minus 2 pi omega w times dot x to k plus first 2 pi t x, the norm of x squared. Yeah. And that means that differentiation will give a factor 2 pi so we claim that the Fourier transform of x times omega to kth equals minus 2 pi to kth omega dot x to the kth, and then the Fourier transform of this guy itself Oh, we haven't come to that yet. I've just now what am I doing here? Take it easy, Jensen. So with respect to the derivative here, I claim that now, do we have any reality check here? First, when k is unity, we differentiate once. That's minus 2 pi. There should be a t as well. And then, yeah, 2 pi, and then, yeah. And then the induction step gives another, and then it should be t as well, pi t and 2, and right, so that should be it. And that means that the Fourier transform of this guy we call what can we call it? G of x, G hat of y. And now we can use part A, because this is what we've got. And the guy we take Fourier transform is this one, and it's well known, except that I don't recall it. It was pi x squared that gave itself, and then we must multiply by a factor t, that's square root t to each of them. So it's t to minus n, square root t to minus n, that's 1 divided by t. Divided by t. And finally, we need to make the transformation. So I look up the transformation formula. It's wrong to call it G, so we call it G tilde. And then G itself is a translation, translated plus U, so it's just it's plus 2 pi I U times dot y, yes, and then the guy G tilde, the Fourier transform of that. Okay, so I did manage to get confused I thought it would be a matter of technique, and it was, but I got confused because I didn't have this present in my mind while I was writing out here on the other side. Well, that finishes what I wanted to do this morning. It's still too early for lunch, so I did the calculation, or redid the calculation to problem B, or part B on paper, and realized that I missed this factor 2 pi to the teeth, which we must divide by here. And that means they cancel. And it's a minus as well. So it's minus I to k t to minus k minus 1 and then this factor I forgot here. I'll just put it in here. Right. Now, we must apply this to this guy. This is actually exactly what they have defined here with m instead of x. So that means that this is just the sum over g of m summing over z squared. So we use Poisson's addition formula. And I should have copied it. It's minus I to kth, t to minus k minus first, e to 2pi u times I, w times I to the kth, when do we sum? Instead of y, I should write m, and then we put the summation in front of it. So we've taken these two and t, right. And it's still m instead of y. And now we shall compare that with the sum here. That agrees, and that agrees, except we have the reciprocal. That's nice. right. Before continuing, I will check this formula numerically. And that was part of what gave me the strength to continue, that I knew that I wouldn't have to carry on without any reality check. So I'll stop the recording and power up Mabel and check this formula. Hi again. It's been a week since the last recording. I wanted to check this formula. And there was another thing that bothered me, which I didn't say at the time, that my derivation in no instance required u to be distinct from, or the coordinates being distinct from integers, rational integers. So as far as I could see, u was allowed to be a Gauss integer. But in the book, Professor Koblitz explicitly excluded that case, and also he used it on the next page to define the function, the Mellin transform, and I didn't see that was needed either. So it was with a trembling heart that I started checking the formula. I wanted to be able to check the digits, change the precision, and then we start taking the result that was some sections ago, and it worked out fine. So this is the one with u as a subscript, and here with u as a superscript. And with t equals 2, the formula fits. That's just divided by t to the first, so no problem there. And we could change this, and it still agrees. We could set k to unity. That's naught, of course, so it agrees again. Now I wanted to try how about 0.0 for u. 4.14, disagreement. So now I went into a rabbit hole trying to find out why it didn't hold when u was naught. I also realized when u is naught, then the two expressions are identical. So it's the same sum. So how on earth does it come about that it could be, one could be minus the imaginary unit times the other one? Of course, it's very simple if the term vanishes, and it is quite easy to see that when k is 1, then when we, or maybe we should rather do it on here. When u vanishes, then these two are identical, so they give the same, always. But when m changes sign, then this changes sign, and that means the sum vanishes. And when it's squared, then we have I times m cancelling with m. But what if it's to the fourth? What happens then? K to the fourth. Here we get something very distinct from naught, but the formula agrees again. So nowhere do we need the fact that u is a non-integer, or not a pair of integers. All right. So now I'm confident this formula holds. So let's go to part D. So we have a character chi, and we must do the usual trick, so we must know the conductor of chi. I did prove that character on the rational integers has a conductor. I believe that proof carries over to characters on the Gauss integers as well. So let its conductor there we go. And that means that in this sum we can write, in this sum we can write x as m times m plus a plus n plus b times I. Where a and b runs through the residue field, and m and n are integers. Now there is a problem here. I would like to, in x to the kth, set m and n outside parentheses. So we need the least common multiplum to do that. So we must define that. What do we call that? Capital T. This is going to be a little complicated. They said we shouldn't do the details, but I need to show that we get a sum like this so that I can actually define the function. Maybe we should just use t and then write it with t instead of. But then it must be t t as well. I think that'll work. So it's t to kth m plus a divided by t to kth, and then the norm of x I'll have to write it. And is that 2s to minus 2s? Now, where were the character? I forgot the character. I can write it here. And now we can just say a point b, a plus ib. There we go. Because T is a multiplum of its conductor. Now, is that true? This is actually not true. When we have the conductor 2 plus 2i, it's then we have t equals 2, but actually we must go up to 4 to get the rational lattice we can use. So it doesn't work to take the greatest, the least common multiplum, as I did here. Well, what we can, instead of constructing it, we can make an abstract argument and say that the residue field is finite, and therefore there's only a finite number of residue values on the real and complex on the real axis, and the generator of that we call T. I claim that for some t, a plus ib will... Now, what's that? That's nonsense. That's nonsense. This is obvious. So that doesn't make sense. That doesn't make sense at all. It was too great. I don't know how to write it. I hope I have explained it sufficiently. And that means that now I should be able to define the function we need. Lambda equals the integral and what we have up here is this and what will come from this. So now we can define the lambda function. So it's t to kth. Let's forget about that. Irrelevant. And then so that's my lambda. Is this an entire function as it is, or can anything go wrong here? And we have the point with this part vanishing when u is in the lattice of integers. This has one term giving unity. And if k is naught, then this gives unity as well. So in case chi is trivial, otherwise it will vanish on naught. And k is naught, otherwise this will vanish. So I believe we only have a simple pole in case chi is trivial and k is naught. Now we shall show it relates to this guy, and it's the usual transformation formula. We use the formula up here, and well, let's write it all. No, that's not what we must do, is it? Let's change variable to 1 divided by s, 1 divided by t first. And then what? Must be 1 divided by t, of course. But then if we use this, well, let's do it and see what happens. I don't see it helps us really. So we said 1 divided by t, then it becomes plus k plus 1, and u, okay, t. I don't see how we come back to this sum. Or rather come back to this integral. I'm stuck here, so it's time for a break. We are into the afternoon now. I have had lunch, bought some goods, went to the shops and done my laundry. Not done it, started my laundry. And I have an idea. Actually, any x, because the residue field is finite, is a group of order the norm of f minus 1, the multiplicative group. We could put it to some order, and then it would be equivalent to, or yeah, any generator we could put to some order, then it would be equivalent to 1 modulo this module. So, ideal f. And that gave me finally an idea to define a character of x by x of the ideal generated by x divided by x, x to nr, x bar to n to nc. I think that is the only way to define it so that it will look like like this series. And all we need to show is that chi bar is a character. And that means that the point, the thing that it's a map into the unit circle follows from the argument before. We can raise x to the power norm of f minus 1, then it's equivalent to 1 modulo f. And that means that x to that power is mapped to 1. So if we can show multiplicativity, then we are home. And per definition, it's x of the ideal of x at y divided by xy to nr xy bar to nc, and since it's ideal, so that's the characters, it's a character on ideals, and that means it's multiplicative on ideals. And then x to nr, x bar to nc, x to x bar to nr. We have come to y, haven't we? Y to nr, y bar to n, that's nc. And then that gives chi-mark of x times chi-mark of y. So that shows why the why a Hecke series has the form when it is over the Gaussian integers. So I don't know exactly what we have been using. As we have been using this, that we get the norm, so that it's a most of order 2 over the rational numbers. I think that's it.